We know that water is a molecular compound. Molecules are comprised of atoms of nonmetals that share electrons. However, water is not your typical molecular compound. It is very unusual, as we've already seen in a previous chapter, but here's another feature that makes it very unusual. It actually decomposes or autoionizes into ions. And these ions are hydronium and hydroxide. Hydronium is a very strong acid, and hydroxide is a very strong base. This is the strongest acid that can exist in water, and hydroxide is the strongest base that it can exist in water. However, the concentration of these ions in pure water is incredibly small. In fact, if we take the concentration of them and multiply the concentration of hydronium times that of hydroxide, we get a really, really tiny number, 1 times 10 to the minus 14th. At 25 degrees Celsius in pure water, this product, this mathematical product of the concentration of hydronium times hydroxide is always, always, always 1 times 10 to the minus 14th. And it has a special name, kW. So when you see kW, what that means is we're multiplying the concentration of hydronium times that of hydroxide, and it always has to equal 1 times 10 to the minus 14th. So in pure water, the concentration of hydronium is equal to hydroxide, and it's tiny, teeny, teeny, tiny, 10 to the minus 7th. So that's 1/10,000,000th of a molar, 1/10,000,000th moles per liter. However, if we have an acidic solution, what that means is the hydronium concentration is greater than that of the hydroxide. Now, when we multiply them together, when we multiply the concentration of hydronium times hydroxide together, it still equals 1 times 10 to the minus 14th. But now, in an acidic solution, we have more hydronium than hydroxide. So hydronium concentrations will be greater than 10 to the minus 7th, and hydroxide concentrations will be less than 10 to the minus 7th. Basic solutions have more hydroxide than hydronium. So in basic solutions, the concentration of hydronium times hydroxide is still 1 times 10 to the minus 14th, but in a basic solution, we have more hydroxide than hydronium. So the concentration of hydronium is less than 10 to the minus 7th, and that of hydroxide is greater than 10 to the minus 7th. So sometimes it's helpful to look at this graphic, which is sort of like a seesaw, where on each side we have the concentration of the two ions that water forms, hydronium and hydroxide. In pure water, these two concentrations are equal to one another. They neutralize each other. However, if we have an acidic solution, we have more hydronium than hydroxide. Again, when we multiply those two concentrations, it still equals 1 times 10 to the minus 14th. But now we have way more hydronium than hydroxide. And then if we have a basic solution, we have more hydroxide than hydronium. Again, when we multiply the concentrations of hydronium times hydroxide, no matter what type of solution we have, the product is always, the mathematical product is always going to be 1 times 10 to the minus 14th, or kW.